Hello children, welcome to another session of PYQ JEE Advanced. So I have put a question on the board from thermodynamics as well as equilibrium concept. So just go through the question. When 100 ml of 1 molar HCl was mixed with 100 ml of 1 molar NaOH in an insulated beaker at constant pressure, a temperature increase of 5.7 degrees Celsius was measured for the beaker and its contents. That was experiment 1. Because the enthalpy of neutralization of strong acid with strong base is constant, which is minus 57 kilojoule per mole, this experiment could be used to measure the calorimetric constant. In a second experiment, experiment 2, 100 ml of 2 molar acetic acid and acetic acid's Ka value is given 2 into 10 to the power minus 5 was mixed with 100 ml of 1 molar NaOH under identical conditions to experiment 1 where a temperature rise of 5.6 degrees Celsius was measured. Consider heat capacity of all solutions as 4.2 joule per gram per Kelvin and density of all solutions as 1 gram per ml. Moving on to the question. Enthalpy of dissociation of acetic acid in kilojoule per mole and pH of the solution after experiment 2. These are the two questions which had appeared in 2020 JEE Advanced paper. So let us go to the question, which is purely enthalpy of neutralization is the concept here. Enthalpy of neutralization of a strong acid versus strong base is experiment 1. And experiment 2, enthalpy of neutralization between a weak acid and strong base. And after all, what do you mean by enthalpy of neutralization? By enthalpy of neutralization, it is the enthalpy change accompanied by the complete neutralization of an acid by base for 1 mole water produced. Kilojoule per mole indicates for every 1 mole water produced, what is the enthalpy change. So what are the processes happening during a neutralization reaction? For example, let us take the problem given here. In experiment 1, you have HCl reacting with NaOH, HCl aqueous reacting with NaOH aqueous giving NaCl salt plus water. This is the basic reaction happening in all neutralization reaction. Acid reacts with base to form salt and water, and the common process happening in all these reactions is H plus liberated by acid, H plus aqueous liberated by acid combines with OH minus aqueous liberated by base to form liquid water. This is happening in all neutralization, whoever be the acid, whoever be the base. So what all the enthalpies involved in enthalpy of neutralization? So enthalpy of neutralization is equal to enthalpy of ionization or dissociation of acid plus enthalpy of ionization of base. Acid should ionize to produce H plus, base should ionize to produce OH minus, and enthalpy of reaction involving H plus aqueous plus OH minus aqueous giving H2O liquid 1 mole. And this value, whoever be the acid, whoever be the base, this part is going to be same value because H plus aqueous plus OH minus aqueous for every 1 mole liquid water formed, and this value is 57.1 kilojoule per mole water formed. whereas this can vary. Now let us take the experiment 1 where the acid is HCl, a strong acid, and the base is NaOH, a strong base. So ionized acid is almost 100% ionized, we say, or its enthalpy of, and it does not require any external help. It does not require any external heat for its ionization, or very negligible, can be taken as 0. So for strong acids as well as strong bases, their enthalpies of ionizations are taken to be 0. So these are negligibly small, otherwise you can take them as 0, so that enthalpy of neutralization involving all strong acid and strong base. Enthalpy of neutralization involving strong acid versus strong base is always a constant, which is minus 57.1 kilojoule per mole. For every 1 mole water formed for a neutralization reaction between strong acid and strong base, 57.1 kilojoule heat would be released. And this data is given to you, and it is said that this particular experiment where 100 ml 1 molar HCl is mixed with 100 ml 1 molar NaOH in a calorimeter. So let us see, HCl 100 ml 1 molar. So number of moles of HCl is 100 ml 1 molar. So 1 into 0.1 or 0.1 mole HCl will provide 0.1 mole H plus ions in solution. Or you have 0.1 mole HCl and number of moles of NaOH is equal to 0.1 mole NaOH. So we know, as per the stoichiometric equation, 1 mole HCl reacts with 1 mole NaOH to produce 1 mole NaCl and 1 mole water. So here 0.1 mole each would produce 0.1 mole water. So for 1 mole water produced, heat is 57.1 kilojoule or 57 kilojoule. It is rounded to 57 kilojoule in your problem. So let us take it as 57 kilojoule. So 57,000 kilojoule for 57,000 joule for 1 mole water produced. Here only 0.1 mole water is produced. Therefore, heat released in this process would be 5,700 joule. For 1 mole water produced, 57,000 joule. Here 0.1 mole HCl reacts with 0.1 mole NaOH. 0.1 mole water would be produced. So number of moles of water produced in this case is 0.1 mole. So here the heat released in experiment 1 is 57,000 into 0.1, which is 5,700 joule. And this data can be used, and using this heat, the contents in the calorimeter, there was a temperature rise of 5.7 degree. Using this data, you can get calorimetric constant, which is essential for the second part of this problem, experiment 2. So let us see what is the calorimetric constant using this. We know Q is equal to ms delta T. So in experiment 1, Q1 is equal to M1, S1 and delta T1, you can say. And Q1 here is 5,700 is equal to, now mass of solution which got heated up. We have mixed 100 ml HCl with 100 ml NaOH, which makes 200 ml solution. Volume of solution is 200 ml, and it is said take density to be 1 gram per ml. So V solution is 100 plus 100, 200 ml, and D solution is 1 gram per ml. So mass of solution M1 is 200 gram. Volume into density, 200 into 1, 200 gram. And specific heat to be, all solution specific heat can be taken as 4.2 joule per gram per degree is given. So S1 is 4.2 and delta T1 rise in temperature is 5. This is only solutions. But this heat is also utilized to heat up the calorimeter material. So we need to put calorimeter constant M2 S2 into delta T is going to be the same because they are in contact. Rise in temperature is going to be same. It will be in equilibrium, temperature equilibrium. Delta T1 itself. Rise in temperature is going to be same throughout. So into 5.7 plus M2 into S2 is the calorimetric constant. Mass of that calorimeter material into specific heat. So that is going to be your calorimetric constant into 5.7. From this, you can solve for calorimetric constant of this apparatus, where calorimetric constant is going to be 5700 minus 200 into 4.2 into 5.7 divided by 5.7. Hope it is clear. From this, calorimetric constant is 5700 minus 200 into 4.2 into 5.7 divided by 5.7. And on doing this, you will get it to be 160 joule. You will get calorimetric constant to be 160 joule will be the mass into specific heat it is coming. So joule per Kelvin, joule per degree you will get. 160 will be the answer you will be getting. Now apply this to experiment 2. In experiment 2, we have a weak acid, acetic acid reacting with the strong base NaOH so that sodium acetate and liquid water are formed. This is the second experiment. Here again, when you write enthalpy of neutralization for this, enthalpy of neutralization is going to be acetic acid being a weak acid, it will have a value for enthalpy of neutralization, which is going to be enthalpy of ionization of acetic acid, which will have a value. And enthalpy of ionization of NaOH taken as 0, negligibly small, plus you have enthalpy of reaction involving H++, enthalpy of reaction involving H++ OH minus giving H2O liquid. Or enthalpy of neutralization here involves enthalpy of ionization of acetic acid. And enthalpy of neutralization minus this value is going to give you enthalpy of ionization of acetic acid. And we know this is a constant value which is minus 57.1 kilojoule per mole. Now let us go to the experimental part of this. Here Q2, experiment 2 Q2 is again equal to M1, mass here M1, S1 into delta T2, temperature rise in the second case, and mass of solution in this, or let us write M2 S2 here. Here, to make a difference, let us put it as M1 of 2 and M1 of 2. Here M2 S2 delta T2 plus you have calorimeters value, which is M2 of 2 S2 of 2 into delta T rise in temperature. Or this Q2 is equal to M2, here mass of solution again 100 ml plus 100 ml, which makes it 200 ml, density being 1 gram per ml, 200 gram, into take specific heat of all solutions to be 4.2 into rise in temperature was 5.6 is mentioned here. Plus this is going to be the same because the same calorimeter we have used. So this calorimetric constant is same as this. So we have put calorimetric constant into 5.6. And calorimetric constant, we already know the value 160. So Q2 is equal to 200 into 4.2 into 5.6 plus calorimetric constant value 160 into 5.6. And when you solve this, this comes out to be 5,600 joule. This is the value you are getting here, 5,600 joule. So for 0.1 mole water formed, it is 5,000 because here again 100 ml 1 molar and 100 ml 1 molar. So 0.1 mole each producing 0.1 mole water. So 5,600 joule for 0.1 mole water form. So what is the enthalpy of neutralization in this reaction? For 1 mole water form, it is going to be 56,000 joule or 56 kilojoule per mole. For 0.1 mole, 5,600 joule for 0.1 mole water form. So in this experiment, enthalpy of neutralization here is equal to 56,000 joule per mole. So for this reaction, enthalpy of neutralization should be written in negative, minus. Here enthalpy of neutralization is 57,000 joule for 1 mole water form. And when a weak acid has come in, the enthalpy of neutralization is minus 56,000 joule per mole. There it is minus 57,000 joule per mole. Here it is minus 56,000 joule per mole. What will be the difference? Difference is nothing but enthalpy of ionization of acetic acid. For strong versus strong, since enthalpy of ionization is 0 for strong acid and taken as 0 for strong acid and strong base, only that constant comes in, which is minus 57,000 kilojoule per mole water produced. And in the second experiment, since a weak acid has come in, the enthalpy of neutralization is sum of the enthalpies of ionization of weak acid, acetic acid, plus this constant. So we got it as minus 56,000 kilojoule per mole water form. So for strong versus strong, minus 57,000 joule per mole water formed. And for weak versus strong, minus 56,000 joule per mole water formed. So the difference is due to the ionization of acetic acid. From here, we can clearly say that enthalpy of ionization of acetic acid or enthalpy of dissociation of acetic acid is the difference between them, which is 1000 joule per mole of acetic acid. Or you can say 1 kilojoule per mole of acetic acid. So your first part of the question, first question is what is the enthalpy of dissociation in kilojoule per mole of acetic acid, which is 1 kilojoule per mole. So option A is correct. That is the first part of the question. So the whole concept is strong versus strong. Enthalpy of neutralization is a constant, which is minus 57 kilojoule per mole or minus 57,000 joule per mole. Whereas if a weak acid is or a weak base is involved, from the heat evolved, a part of it will be utilized for ionization of the weak electrolyte. Here acetic acid has utilized the difference 1000 joule per mole for its ionization. So your answer is 1 kilojoule per mole. Coming to the next part of the question, the pH of the page like second part of the question, what is the pH of the resultant solution is the question. So first let us see what is the concept to be used to find the pH of the solution. To find pH of the solution, the concept to be used. Let us see whether to use left behind basis pH, or is it a salt hydrolysis concept, or is it a buffer concept. So let us see who all are formed here. We are provided with 100 ml 2 molar acetic acid and 100 ml 1 molar NaOH. So we are provided with 0.2 mole acetic acid and 0.1 mole NaOH. Second experiment. Now, in the previous experiment when we discussed, we said 0.1 mole acetic acid reacts with 0.1 mole NaOH because their NaOH was the limiting reagent. So, from 0.2 mole, only 0.1 mole acetic acid will be utilized to produce 0.1 mole water in the second step because NaOH was the limiting reagent. Now, on the whole, what all are there in the solution? Let us see. During this reaction, when acetic acid aqueous reacts with NaOH aqueous, giving sodium acetate aqueous plus H2O liquid. What we have here is 0.2 mole of acetic acid is here and 0.1 mole NaOH is here. So that what will be produced will be 0.1 mole sodium acetate because sodium hydroxide is the limiting reagent here. 0.1 mole sodium acetate and 0.1 mole water would be formed. So in the final mixture, we have water, we have 0.1 mole sodium acetate. All the NaOH would be consumed because that is the limiting reagent, and from 0.2 mole, only 0.1 mole acetic acid would have been consumed, leaving behind 0.1 mole acetic acid in the final mixture. So here in the final mixture, in 200 ml solution, you have 0.1 mole acetic acid in it and 0.1 mole sodium acetate in it. The concept is buffer, acid buffer. The final mixture contains a weak acid and its salt with a strong base. So it's an acid buffer. So to find pH of an acid buffer, we can use Henderson equation. And by Henderson equation, to find the pH of an acid buffer, Henderson equation to find the pH of an acid buffer, pH is equal to pKa plus log concentration of conjugate base, or you also call it concentration of the salt, divided by concentration of acid. pH can be calculated using pKa plus log concentration of conjugate base or concentration of salt by concentration of acid. And to find pKa of acetic acid, we are provided with Ka of acetic acid is 2 into 10 to the power minus 5. And pKa is negative log Ka, which is negative log 2 into 10 to the power minus 5, which is 5 minus log 2, which will come out to be around 4.7. Log 2, 0.3010. So, your pKa of acetic acid will come out to be around 4.7. So, pH is equal to pKa 4.7 plus log concentration of conjugate base, number of moles of salt 0.1 divided by volume, which is 200, divided by number of moles of acid left behind 0.1 by same volume 200. So 0.1 by 200, concentration is number of moles by volume in liter. So here volume in liter 0.2. So you have 0.1 by 0.2 divided by number of moles of acid in the mixture is again 0.1 mole acetic acid. So 0.1 by volume of solution is 0.2. So numerator 0.1 by 0.2, denominator 0.1 by 0.2, it comes out to be log 1. And we know log 1 is 0. Therefore, pH of the resultant solution is 4.7. So, out of the given options, the pH of the solution at the end of the experiment, option B 4.7 is here. So, whenever you get such pH questions, you have to be very careful whether left behind strong acids or strong bases, concentration is to be determined and get the pH, or is it a salt hydrolysis concept or is it a buffer concept. Here we found that final solution has some weak acid and its salt with a strong base. So definitely it's an acid buffer. So we went for Henderson equation to find the pH of the solution. Hope this session was clear to you. Thank you, children. Thank you.